Can you see the presentation?
Excuse me, Aleida, did you start the recording?
Yes,
Okay.
yeah.
Oh, okay, thank you.
Yeah, it takes some time to appear yeah.
Thank you.
Can you see the presentation, Aleida?
Yes.
Yes.
Okay, so thank you very much. My colleague Irene and me are going to present the implementation of the bamboo solutions in the steelmaking sector. Maybe first a short introduction about ArcelorMittal. ArcelorMittal is one of the largest steelmaking company. Indeed, it's the largest one, the most important manufacturer in North America, South America, and Europe. We are present in 17 countries with more than 168,000 employees last year, with a production of 58 million tons of iron ore and more than 17 million tons of crude steel in last year. Okay. We have indeed 12 research centers all over the world. We belong, Irene and me belong to the center in Spain, Global R&D Asturias. And one of the key strengths of ArcelorMittal is that we have more than 200 trade-market products and more than 600 patent families. Okay. So within this presentation, we are going to make first an introduction about the steel making process. Then we're going to explain within the bamboo strategies why we're going to cope with the waste heat problem and the potential of recovery energy from process gases in terms of decarbonization. And we're going to present both technologies, heat pump and flame monitoring case that we have developed together with different partners of this bamboo consortium. And some of the technologies have been presented this morning in detail. And we're going to make the presentation for the implementation in the steelmaking sector. Okay. So starting with the general process explanation, steel indeed is an alloy of carbon and iron. In weight, carbon is typically or is less than 2%, typically less also than 1%. And there are three main routes to manufacture this steel. The most important one in terms of production is the integrated route, based on large facilities such as blast furnaces and converters. And in addition, steel is also manufactured, is also recycled from scrap and by means of melting it in an electric arc furnace. And finally, the direct reduction route that at the moment represents a small fraction of the small share of the tonnage, but has quite huge potential in terms of decarbonization. So basically, and I will put the pointer. So basically, to produce steel from the integrated route, we require carbon that comes from the coal and iron that is in the nature form oxidized in form of iron ore. So in both sinter process and coke plants, we transform these raw materials into the right elements to be introduced in a huge reactor, that is the blast furnace, from which we produce a kind of liquid iron. And this liquid iron is further reduced in a Linz-Donau process, the BOF process, by injecting oxygen. Okay. Then this in that case, we generate liquid steel. It's then casted in forms of semi-products, typically slabs, blooms, billets. Okay. Another route is the direct reduction iron. We directly reduce the iron fines using coal and also reducing gas. And this solid products is then melted in an electric arc furnace. On the other hand, if we take a scrap from recycling steel, we can also melt the scrap in the electric arc furnace. At the end, we have liquid steel that we need to cast and then give shape forming typically by steel rolling processes. The first part of the process we call the upstream or primary process, and the second part, okay, we call it downstream or finishing processes. So the problem is that steel making is a very energy-intensive process. Okay, we require huge amount of fuel gases, of steam, of electricity, apart from the coal that not only gives the required carbon for the steel, but also provides energy. And we would like to, or we are, our companies trying to reduce the energy consumption. Okay, also trying to replace fossil fuels. And Bamboo projects provide some solutions, a couple of solutions to work with it. So in detail, if we take a look to the primary operations that we presented before, in the coke plants, we take the coal and we generate the coke, that is the raw material for the blast furnace, and as a byproduct we produce what we call coke oven gas. It's the heating value of this coke oven gas is more or less the half of the heating value of the natural gas. It's very rich in hydrogen, and this gas can be used, or we try to use within our processes as much as possible. On the other hand, in the blast furnace process, apart from the liquid iron, we produce huge amount of energy of a very lean gas that is called blast furnace gas. The heating value of this gas is about 10 times lower than the heating value of natural gas. So we require huge amount of volumes to generate the same amount of energy than natural gas. And finally, the converter gas that is produced during the basic oxygen furnace. With this gas, sometimes is directly used inside of the converter to generate the steam. In other cases, recover and introduce in the gas grid. So one of the goals of this Bamboo project is try to use in a high efficient way these process gases, coke oven gas, blast furnace gas, and converter gas, trying to replace natural gas. But apart from that, in this as energy carriers, we require coal, we require electricity, and we require also steam. So these utilities are used also in the rolling operations. We take the semi-products, for example, the slabs, and we need to manufacture a thin coil. And for that, we need to preheat to reheat this material in furnaces that we call reheating furnaces. We require also steam in several parts of the process. And finally, our main products are coils, are sections, beams, tubes, rods, plates, wire, etc. Okay, so this is a general overview about the steel making process. And now my colleague Irene will explain a little more about waste heat and process gases potential.
Yes. Hello everyone, this is Irene speaking. Well, as Victor commented, we are one of the highest energy intensive sectors, but in this slide we need to remark 2 points. One is that from all of this total energy consumption, around the 20% is lost in the form of waste heat. But also, as also Victor commented, we produce several process gases that we use to produce heat or electricity. And according with the World Steel Association, if we fully reduce these process gases, we can also provide between the 60 and the 100% of the total plant's electricity requirements. One moment. So if we reduce our process gases and we recover our waste heat streams, we are supporting in the decarbonization process that is highly important in our sectors because our process is based on the use of fossil sources. Okay, for example, we need 780 kilograms of coal to produce 1 ton of crude steel, but also we use considerable amounts of natural gas for combustion purposes. Okay, for example, used as a fuel in the reheating furnace or in the brews. So with the objective of reduce these CO2 emissions, we are participating in the Bamboo project based on two lines of research. One is the use of waste heat sources to produce steam via the heat pump integration, and the other is reducing our processes gases via the flame monitoring system that it's easy to do a combustion and also is more efficient, okay? Both lines are according with the strategy of ArcelorMittal of reducing the CO2 emissions in the future. Well, if we need to do a zoom in the waste heat sources and in the distribution of the temperature of the sources, because the volume, the temperature, and the easy to recover these streams are relevant factors to evaluate its potentiality. As you can see in the picture, in the global industry in Europe, the main waste heat sources are in the range of less than 200 degrees Celsius. But if we translate this to the steelmaking processes, it changes a little bit. So from one side, one of our mainly streams potentiality are in the range of the high temperature, more than 5 degrees. Some of our solids, basically in solid products, for example, the final products or the byproducts, has temperatures more than 1000 degrees Celsius. But the thing is, there are high complexity to recover the heat from the solids because the full cost-effective technologies are yet under development. The other streams that it's important in this range of temperatures are the fumes that we obtain from the reheating furnace. We have a lot of reheating furnace in our facilities. That is a stream that is more affordable to recover. Even more, initially we recover part of this heat to preheat, for example, air combustion or to preheat processes. Well, on the other hand, we have a forgotten stream that is the low-grade range streams, basically based on water streams, because we are huge consumers we consume a lot of volumes of water to clean and to cold our final products in the processes. But we don't explode these streams because sometimes these low-grade range streams can cover the high demanding requirements of energy that we need in the process. Okay? Well, parallelly to this loss of energy in form of waste heat, we also are huge consumers of steam. Our steam consumption can account for around 10% of the total energy consumption in the iron and steel industry. And we use steam mainly for the process heating. We use steam to heat mixtures, to heat water, air, for lubrication. Okay? In some plants, one of the facilities that we have, that is the steel shop, can produce part of this steam and could be integrated in the steam network of the plant. But this is a small fraction in comparison with the steam that we need to boil. Normally, the steam that we use is generated in external boilers from the process gases and from natural gas as well. Other important point here is that we generate the steam in a centralized way. So we need to distribute then this steam to all the points of the plant. And this is associated with some losses that at the end are translated that are waste heat loss, okay? So it's important to take into account that we need to transport the steam from our generation point to the final consumers that are around all the plant. Hence, if we decentralize in some points this generation of steam and we reduce also the generation of steam by conventional boilers, we can obtain some advantages from a point of view, from an economical and environmental point of view. Well, so in this point, it comes into play the heat pump technology. This visual scheme it comes from AIT, that is a visual way to represent the heat pump functionality. And as I just commented, we are huge consumers of steam, but also we have a lot of potential in the low-grade waste heat streams. So we are really interested to look for technologies that produce steam in a green way using our waste heat sources. Okay, the heat pump not only meet this criteria, but also is able to upgrade our low-grade streams to give us the energy requirements that we need and to produce the steam with the high quality that we need. Obviously, always giving a reduction in the CO2 emissions because we avoid to produce steam in a conventional way with the boilers. Well, to achieve this goal, we identify an industrial application in our processes, particularly in the picking line facility. In this facility, we need to heat the ASIC tanks, okay? To keep a constant temperature, we heat this ASIC with the steam, and we need to keep a constant temperature here, with the finality of remove scale from the final products. So our idea is to preheat the ASIC in the piping before the ASIC tanks, okay? So to do that, we use we identify two types of streams in this facility as input in the heat pump, apart from the electricity. One is the condensates, the current condensates of the steam network that currently are stored and discarded. So we use the heat to give heat to the evaporator in the heat pump, and the other streams are the condensates from the circuit of the heat pump. It means that the heat pump generates steam. The steam goes to heat the piping of the ASIC, and the condensates are recirculating in a closed circuit to go to the condensator, okay, part of the heat pump. Also adding some of the make-up the mineralized water. So we have worked in the integration of the heat pump in this industrial environment, and it could be a clear example of the use of high, low-grade potential streams in the steelmaking sector to cover some part of the necessities of the steam, always reducing the CO2 emissions and also reducing the cost of the utilities due to the avoidance of using steam produced by conventional boilers. So, and now my colleague Victor continues with telling you about some combustion monitoring opportunities.
Yes, so the second technology that we would like to develop is to evaluate, to monitor in a more efficient way the combustion processes. In this case, focus on firing process gases. So we have the goal of achieve a higher efficiency in the combustion. We see here, for example, from the literature, we can find some course of the impact on efficiency in terms of, for example, the excess air that we use in our furnaces. Also, that has an impact on emissions, and we would like to use as better as possible our process gases. So this combustion monitoring, we expect that we can achieve a better efficiency in firing, a better use of our own process gases, in that case reducing the external purchasing of fuel gases such as natural gas, and finally we expect also to have an improvement on the heating quality. So the way of doing that, together with CIRCE, we have evaluated how we can monitor a flame, an industrial size flame, in a pilot furnace that we operate within ArcelorMittal R&D. And this combustion furnace chamber, we provide some holes, okay, so that we can introduce a flame monitoring camera. CIRCE has evaluated what is the best technology of doing that. This morning, Anna made an explanation about how this system should work. And we have supported them in the definition of the position, the camera cooling, all the protection system. We need to take into account that process furnace operates 24/7. So we need to be sure that in case of a failure, for example, of power supply or one breakage of the cooling, we need to protect the system by extracting it. And the idea or the goal right now is to carry out a testing campaign evaluating different process conditions. So we're going to fire different fuel gases We are going to evaluate different process conditions in terms of excess air, so lean conditions, rich conditions, the impact of oxygen enrichment, and the impact on process parameters such as temperature or preheated air temperature. And with the goal, as explained before, to develop a flame monitoring system that would allow us to operate our furnaces in a more efficient way.
Yes, so regarding the next step, regarding the heat pump, the idea is the application that we have defined and identified is test the heat pump in a ArcelorMittal industrial environment. So testing in the picking line facility to produce steam with the condensates, okay, in order to heat the part of this acid that goes to the acid tanks.
And regarding the
webinar del mio progetto.
Regarding the flame monitoring system technology, the next steps are based on evaluating several process gases combustion and several operation conditions, and our partner CIRCE will develop and validate a flame diagnosis algorithm based on the information provided by us, okay, so that we can test in an industrial environment this solution from the Bamboo project. So that's all regarding the presentation. I would like to thank you for your attention, and as Aleida and Cristina explained before, if you have some questions, please feel free.
Okay, thank you very much, Irene and Victor. I don't know if any attendee has any question. There is no question in the chat, but maybe you can directly ask them any doubt you may have. Okay, so if there is no question at this moment, we can move to Cupra's presentation. Our colleague, Mr. Kandemir.
Hello. I'm opening the presentation from my computer, right?
Mm-hmm. Yeah.
Okay. I think everyone can see.
Yes.
All right. I am Can Demir from Tüpraş R&D Center. I am working in the Project and Technology Management team of Tüpraş R&D Center. And I am working in Tüpraş since 2017. Tüpraş is Turkish Petroleum Refineries Corporation. It has 4 refineries inside Turkey, and it's the biggest player in the refining sector of Turkey. And Tüpraş is also the largest enterprise of Turkey by revenue. It has an annual refining capacity of 30 million tons and total storage capacity of 8 million meter cubes. And the biggest refineries are in Izmit and Izmir. They have about 10 million tons of yearly crude oil processing capacity, and Kırıkkale has 5 million tons, and Batman is somewhat smaller refinery, which only produces bitumen for road production. And Tüpraş has a total of 5,400 employees. And Tüpraş refineries has a high Nelson complexity. Nelson complexity is an indicator of how complex a refinery is. In fact, how effective can a refinery convert crude oil to white products is shown by Nelson complexity. And the Nelson complexity of Tüpraş by all refineries is 9.5, which is compatible to refining companies of Europe. In fact, Tüpraş was a state company until 2005. In 2005, the Koç Holding, the largest conglomerate of Turkey, have acquired 51% share of Tüpraş and owns the management rights. And the other 49% is on stock exchange market. And of course, after the privatization, many investment projects have been carried out, and Tüpraş refineries have been modernized with respect to needs of the customers and the markets. And the most important project was the establishment of Residuum Upgrade Project in 2015, which is a refinery which converts I can say which converts the undesired, let's say, products to more desired products such as benzene, gasoline, LPG, and this investment was worth $3.2 million, but it have gained Tüpraş advantage in the market. And Tüpraş R&D Center have been established in 2010. Tüpraş R&D Center is responsible for the R&D activities of all Tüpraş refineries. In 2011, we have got our first EU project inside the 7th framework program, and in 2014 a new campus have been opened, as you can see from the slides. In 2016 we have received SPIRE membership, and in 2019 Tüpraş have become the most successful Turkish company in Horizon 2020 with 16 Horizon 2020 projects. So we can say we are somewhat experienced in Horizon projects. And last year we have realized the first commercial sales of fully R&D developed products. In refining sector, developing new products is not easy because approximately all products have very strict specifications. You have to conform those, but creating new products such as some special fuels or some special bitumen is not an easy job. So it took about 10 years to develop a new product to the market and commercialize it. What are the R&D focus areas of Tüpraş? The most important triggers are in the recent years environmental triggers, mostly carbon capture, utilization and storage, water and waste management. In fact, the trigger of a bamboo project is also in fact the waste heat recycling, for example. It's one of our R&D focus areas. In green hydrogen, industrial symbiosis, renewable energy and fuels, energy efficiency, reaction systems, pilot plants, hydrocarbon and material characterization, and fuel product material development. And also we are carrying out studies on advanced data analytics, modeling, sensor and robotics technologies. Those are our projects right now. Bamboo project that started in 2018. And as Tüpraş, we are in the bamboo project as a petrochemical real demo site. with close cooperation with Turboden, we are planning to install a ORC system, organic Rankine cycle system, which will use one of our waste heat streams as an energy source and make electricity out of it. I will give technical and information about this application. In our Izmir refinery, the refinery which Bambu project will be implemented is the Izmir refinery, not Izmit refinery. In fact, the R&D center is in Izmit, and I am in Izmit right now, but the project will be implemented in Izmir refinery. Izmir refinery is also one of the biggest refineries of Turkey. It has similar capacity to Izmit refinery. In fact, before the project, we have carried out investigation of our waste heat streams. We have investigated which stream we can use, which stream suits the most to Bambu projects. And at the end of those investigations, we have found a stream seems very suitable for the Bambu project. That stream was the atmospheric dip side stream of the Izmir refinery's U100 atmospheric distillation unit. To give some summary information about the atmospheric distillation units, it's the most fundamental unit of a refinery. In fact, it takes the crude oil as the raw material and distillates the crude oil, and it cuts the crude oil into fractions. The lightest fraction, which is LPG, is taken out from the top of this atmospheric distillation unit, and the most heavy side products are discharged from the bottom of this atmospheric distillation unit. And the heaviest side stream, the heaviest product of this unit, is the atmospheric dip side stream. It's so heavy that it should be at a specific temperature to be able to flow through pipelines. It should always be, for example, higher than 18-19 degrees C. Otherwise, you cannot transport it through pipelines. And in the existing projects, existing process, this atmospheric side stream, there is, in fact, in the original plan, there is an inefficient way of cooling this atmospheric dip side stream. It's cooled by air cooling fans, as you can see in the slide, and it's cooled to 120 degrees C before being sent to vacuum distillation feed tank. The vacuum distillation feed tank is the, in fact, raw material tank of the vacuum distillation. In vacuum distillation, the atmospheric dip side stream is further distillated under a vacuum, so that it's distillated in a more efficient way. In fact, in refineries, heat integration is very important, because, the designers do their best to make use of all the heats. So, in fact, one an output of a unit is heating an input. For example, there are many heat exchangers that ensures the heat integration. But in this case, in order to not make it too complex, the designers of this unit have decided to use air cooler fans to cool down this atmospheric tip side stream. But of course, it's an inefficient project. The heat goes up to atmosphere basically. So important amount of heat is lost to atmosphere by this way. And when bamboo projects have first the consortium have started to form, we have spotted this stream to be used in the project. And this slide is about implementation of the ORC system, and we are planning to install the organic Rankine cycle turbine system, which will be developed by Turboden in the Izmir refineries U100 atmospheric distillation units. So that the atmospheric dip side stream, which is a hydrocarbon stream, will be input to the Turboden's organic Rankine cycle turbine system. As Turboden Tommaso have explained it, it will be using the heat of this, the wasted heat of this atmospheric dip side stream, and it will generate electricity with a rate of 1.8 megawatts. So if we think about the whole year, it will make 10 megawatt hour per year energy out of waste energy. So if we make a rough estimation of how much carbon dioxide emission it will prevent, so that makes 6 kilotons per year. So it's a very good deal of amount for carbon dioxide emission reduction. And what we have done so far is we have decided on the place of this unit. We have spotted the area. The ORC system will be placed in this area, and it will be flattened, and the ORC system will be stand upon this area. It will be taking the atmospheric dip side stream as input, and in a closed loop, it will use a turbine system and create electricity. So hopefully in 2022 we will be seeing the first result. We will be installing this system. Right now Turboden will be starting the production, the manufacturing of the system, and at the same time as Tüpraş, we are preparing the area, we are preparing the utilities and every kind of necessity to be able to install and commission this ORC system. So that's end of my presentation. Thank you very much for listening. If you would have any questions, I will be gladly answer. Thank you.
Thank you very much, Kaan. Okay. Does any attendee have any question to Mr. Kandemir? Okay, then we can move to pulp and paper presentation. So Raina, is your turn.
Hello together, ladies and gentlemen. It's a pleasure to participate in this event today. And I'm glad to show a little bit what we have done in our demonstration plant within the bamboo project so far. So I hope my presentation, my slides are visible.
Yes, we can
Is it
see
okay?
them.
Great. For those of you who have been participating in the session this morning and who have listened to Erika, Erika told a lot of topics which will be also part of my presentation this afternoon. Within Bamboo, we are looking for, or we are developing strategies and try to implement technologies to integrate regional renewable energy surpluses within this German, which come up within this German Energiewende. I want to talk about some words about UPM, the Biofor company, then talk about the challenges which we face within the German Energiewende with its more and more volatile power generation and the decrease of the conventional constant power generation assets. Our case where we check the utilization of the regional photovoltaic generation in combination with an energy-intensive industry site within this area, and then the UPM communication papers approach within this German Energiewende. What about UPM? UPM is a Finnish-based company, and we see ourselves as front runners in forest industry. Out of the raw material wood, we provide renewable solutions for a high variety of end uses. We invest in sustainable growth and innovate for a future which will be beyond the fossil area. We feel high responsibility as a core of everything we do. Our products are, in a nutshell, fiber products from biomass, from wood biomass, molecular bioproducts, also from wood products as basics, meaning sawmill, timber, and so on, and also low emission energy. These are the cornerstones of our business, which is a worldwide business. In 2020, we had a turnover of close to 9 billion euros, and from our wood-based raw materials, we are feeding 7 business areas: biorefining, energy, label material in UPM Raflatac, UPM specialty papers for special paper usages, UPM plywood, and our new businesses. We have 51 production plants all over the world and 18,000 people in 46 countries in the world are working for UPM. We are producing renewable and recyclable products for packaging, labeling, transportation, electrification, construction, and so on and so on. I think people who are interested can get the material of this presentation and all the other presentations after this event. I am working for UPM Communication Papers. This is this is the biggest business area from UPM. This is one of the traditional business areas from UPM, and currently we are responsible for at about half of the turnover, of the annual turnover. Our business is a declining business, meaning the demand, the paper demand for this kind of paper we are producing is declining. All the office papers, all the newsprint papers and the magazine papers see a rather significant decline over the last 8 years, a decline which has not been ending yet, but and will continue as we see it. Nevertheless, we believe in a future of paper, and therefore we try to enable our production sites to come into this future with this increased requirements for climate protection and energy efficiency on one side. On the other side, with the earnings from our traditional business, from communication papers, we are also financing all of our development projects, which are several ones at the moment. Coming now, maybe one step back to myself. I'm responsible for the energy topics here in Western Europe area, which is from the British island via France, Germany to Austria. Coming now to the challenges which we see in the development of renewable energies in Germany. We started this challenge, I would say, more than 20 years ago, when we established the first photovoltaic and the first wind generation units in Germany. Nowadays, these renewable power plants, photovoltaic and wind, represent more than half of the installed capacity in Germany. These main pillars of the renewable generation assets, they show large fluctuations and volatility, and therefore we are faced with the challenge to completely redesign our energy system coming from a system from centralized power plants, which produce whatever power demand was. We are now changing into a world from volatile, fluctuating power generation, and we have to adapt the demand more to the generation, and we are getting less and less conventional power plants, which produce according to demand. In order to increase the renewable power generation in the next 10 years, in the next 20 years, until 2040, and finally then until 2050, we talk about the factor 6 of the current installed capacities. This is a rough figure. There will be operational changes required both from the generation side, but also from the demand side. As long as we do not have a reliable generation or storage for this renewable power, which we have surpluses to certain times in the year, in the day, the distribution of this electricity from the renewable energies is crucial. So therefore, at the moment, we are working on the challenge. You see here Germany in the renewable world as we see it at the moment. We have a huge amount of onshore and offshore wind power generation in the northern and northeastern part of Germany, and we have a huge and constantly growing amount of photovoltaic generation in the south of Germany. This brings completely new challenges for the big transmission grid operators, who have to take care to transport the big surplus of renewable wind generation from the northern part of Germany, where we have not a lot of industries currently concentrated, to the southern part of Germany, who has close to zero, or only a few wind generation assets, and also the wind situation is completely different to the northern part of Germany, and therefore this huge surplus of wind generation from the northern German area to the southern German areas where a lot of industry is situated is the challenge at the moment. There is a lot of investments going on at the moment. Investments which is one side of the story. The other side of the story is the acceptance side of the story of this big infrastructure measures. Meaning everybody who is living close by to this big transmission lines from north to south is not very happy about it, and therefore there's some timely delay. When we have here a realistic view on this, the realization of this big transmission lines will take some additional years, and whenever they will be ready, the increasing generation capacity until this time will need most probably additional transmission lines. So therefore, we have been looking to find solutions that we can live and utilize the system as we have it so far to survive with our assets, with our power consuming assets in the southern part of Germany. Therefore, that we try to utilize the regional photovoltaic generation in our industrial sites, and this needs a lot of additional flexibility in consumption and also in the power generation capacity or behavior which we have in our industrial power plants. We found out, or our idea is that our flexibility on consumer side can contribute significantly in the stabilization of the power grid, meaning we see our assets capable to reduce the need for this power transmission from south to north and backward. We have made some investigations with some grid operators that the regionally, which show clearly that the regionally produced photovoltaic can be used directly in the region where it's generated, and we would avoid there this long distance transport, which besides the fact that we don't have this transport capacities yet, whenever we will have it, it's also a question of losses, even in this high voltage DC transmission way, which it is planned. The on-site fossil fuel-based generation in the industrial sector, as in our ones, which has a high CHP potential, therefore can be substituted partially by this renewable supply, by this volatile renewable supply, and the next step would be then the electrification of the heat generation, which is nowadays done by the fossil fuels. What our investigations so far have shown is that if we keep our industrial site, including a demand asset and also an industrial power plant fired by fossil fuels gas, when we operate completely flexible, 100% of the electricity can be utilized from the region around the mill site, 100% of renewable generated electricity could be utilized in the mill. So this, without going to a lot of details here, the dark blue points. This is the situation without our flexibility actions, and the light blue part is the situation when we only operate the industrial power plant flexible. So this is the first part which we have had a look on. So for example, the grid load will increase, the regional grid loads will increase by almost 50% until 2035 by the increase of renewable photovoltaic generation. And if we flexibilize our industrial power plant operation, we can keep the grid load on current level even when we double the photovoltaic generation capacity in this area. Nowadays, we export 49% of the PV generation, and until 2035 we would export 70% of this PV generation, export it to this high voltage grid lines to the north of Germany or to any other areas in Europe. We could reduce this power exports from this area by flexible operation of our power plant down to 20%, and so on and so on. How will we do this, and what will be the next steps? This is a schematic view of such a paper mill embedded in a generation situation around the mill. Let me show the pointer. So a paper mill exists from first of all, of course, a raw material side, a pulp generation or a pulp production asset, and a paper machine. Pulp and paper machine, they both need power and heat to produce paper, and this heat in a traditional way is generated normally by heat-only boilers, meaning burning natural gas to deliver heat, and by an industrial power plant which is on highest efficiency level, consisting from a gas turbine, a heat recovery steam generator, and a steam turbine. Both gas turbine and heat recovery steam generator heated by natural gas. And outside of the mill, we have either photovoltaic generation or windmills, depending on the location of our mill. And currently, our demand from power, which is not generated on the own industrial power plant, comes from the public grid, which is fed still by coal and gas and nuclear power plants. Our idea is now, with the increasing surplus of photovoltaics around the area, to operate this industrial power plant higher flexible than we did it in the past, and try to go here into a part load operation to produce, to generate only a minimum amount of the power by this traditional way of power generation, and consume as much as possible from this solar generation around our mill, from the region around our mill. When we go to this flexibility options, which Erika described a little bit this morning in her presentation, I clustered it a little bit in flexibility levels, which we have in such a paper mill. The level 1 I see in this industrial power plant with this high efficiency. These flexibility levels, we are already, let's say, operating it to a rather high extent. We can increase it a little bit more, but we are one of the big flexibility providers within Germany, within the German energy intensive industry, and therefore we have done a lot of our homeworks. The level 2 is the demand side management, meaning we steer the consumption of our demand assets, mainly here the pulp production side and the paper machine, depending on the availability and the volatility of the renewable generation situation. Also there, we have almost all assets in this demand side activity markets, and also there a lot of homeworks are done. But and this is to say, this level 1 and level 2 flexibility options, they are mainly focused on supporting the grid, meaning they are prepared for a situation that there is not a surplus of renewable generation in the grid, but a deficit of renewable generation in the grid. Meaning these level 1 and level 2 flexibilities, in the majority, not totally, but in the majority, in the major part, they act so that we increase the power generation in the industrial power plant if needed, if the system, the grid system, needs support, meaning there is a deficit of renewable generation in the grid. The same in the level 2 demand side management. We are able to decrease our electricity consumption from the grid if the grid cannot supply, or the grid stability is in risk when not enough renewable generation is in the grid. What we are looking now in this bamboo is to intensify this level 1 and 2 flexibility options, but to look in the level 3 and 4 flexibility options. These are options which go to the other direction, meaning which cope with the situation that we have a big surplus of renewable generation in the grid, and which we cannot, let's say, cope in a big amount with our existing assets at the moment. So now in the level 3, we talk about new electricity consumers, which we aim to electrify heat generation. Meaning a heat generation which is traditionally done by fossil fuels, really shift step by step to electrification, and additionally to this electrification approach, which can be done, for example, by power to heat units, which can also can be done by heat pumps, to add also some storages. And only then, when we have installed these capacities, I would see us in level 5, where we would combine all the opportunities, where we have then the highest flexibility range from 0 to maximum. Within Bamboo, we are now working on identification of waste heat sources to utilize in a possible installation of heat pumps. We are working on definition of technologies for heat generation, either power to heat or heat pumps, and we in the next step to define possible storages, both for heat and electricity. This is the same principle or the same schematic, only as an example. What is the scientific approach from the involved partners in this Bamboo project? We see on the left side the production assets with their demand situation, and the different demand assets. So we are working on identification, clustering, and prioritization of waste heat sources. We will define the preferable technologies for heat generation from electricity in combination with storages, and then do a feasibility study for sustainability and profitability of possible investments in this electrification of the heat generation. The flexibility requirements in context of German Energiewende, and who was following Erika has heard a lot more than that. What I see now as flexibility requirements. I see the following 5 requirements as a must for flexibility. Are they technology-wise possible? Are they necessary for the system? Do they have any advantage for the economy or for the society? Are they economically attractive? And do they bring their effects on sustainability as early as possible? Having a look on our UPM demo case, which we are checking at the moment, technological possibility. It's possible. We know our demand and generation flexibilities, and the electrification technologies we are talking about are either existing when we talk about power to heat, or on a good track to be developed to the purposes and to the demand which we need, meaning high temperature heat pumps, for example, meaning some storage opportunities. Systemic necessity, I would say yes. We are delivering a good opportunity to keep the grid stable, to keep the grid stability on the regional level, and to avoid unnecessary investments in the regional but also in the transmission grids. This is also the case in the advantage for the economy. we decrease the investment needs in grid transmission and maybe additional generation systems by our existing mills, by our demand assets, but also by our industrial power plants, which we try to integrate in this renewable energy generation world. From the economical point of view, we avoid an increase in the grid cost system for all, not only for us, but for the society, because investments in the grid which would be needed without our involvement, without our flexibilities, have to be paid by the public, have to be paid by all the consumers. And about the best time effect on sustainability, we are talking on let's say existing assets, which we do not have to make huge investments, existing assets which can be completed by available technology investments with a high efficiency and with an immediate effect, or with a close by effect time-wise to the CO2 emissions. What we face by the development of this topic is we have to ask for essential requirements. The regulative framework, which is in constant development, has to be developed and implemented to such cases without negative effect for the economic side. We have to trust into our investments, meaning when we have the regulative framework, it cannot be the case that it's changed significantly or completely within a 5 years period. And we have to keep our international competitiveness, which is more and more relying on some regulative exemptions and regulative frameworks, which can be changed in a very short time frame, and which could enable us, or which should avoid our international competitiveness. So overall, we are happy to participate in this bamboo project, and we see us well in communication and well supported by all the involved partners which we are working with. Thanks a lot. I think I'm in time.
Yes, thank you very much, Rainer. Thank you very much for this very useful and interesting presentation. I don't know if any attendee has any comment or question. Okay, so yeah, thank you very much. We can move then to our last presentation with Mr. Harris from Grayson Magnesite. Okay, we can see your presentation mode. Okay, thank you very much, Harris.
Okay, good afternoon. I'm Harris Giannoulakis. I work for the Research and Development Center of Grayson Magnesite in Thessaloniki, Greece. As the last presentation of this day, I will talk about decarbonization at Grayson Magnesite by replacing petcoke with biomass. There has been a lot of talk today about the challenges of energy-intensive industries. I will not go through this again. However, I would like to stress that there are several types of energy-intensive industries, like cement, lime, magnesia, sintered lime, ceramics, glass and steel. And note that they involve the generation of flue gases with temperatures of 1100 up to 1800 degrees Celsius or higher. And these lead to CO2 emissions, mainly from the combustion of fuels, but also from the decomposition of carbon and raw materials, which are called inevitable process emissions. For the case of the steel industry, there is also the use of carbon as a reducing agent, which will lead to the generation of CO2. Even if we increase our dependence on variable renewable energy resources, which is the ideal outcome, we will still have the CO2 emissions from the carbon raw materials, which, as I said, are the inevitable process emissions. For bamboo, Greza magnesite serves as an example case and a demo site. We fall under the category of non-metallic minerals. We are producers of natural magnesia or magnesium oxide, and as you have understood, we are an energy-intensive industry. This is an aerial photograph of the Gerakini mine installation, a detail of the calcination plant, which is also the bamboo demo site. A few things about Greza magnesite. We operate a mine and installation at Chalkidiki, which is in the northern part of Greece. We also have large concessions in the island of Evia in central Greece, and also installations and mine site in Turkey in the area of Eskişehir. Our consolidated sales volumes are 235,000 tons per year of magnesia products. We employ around 400 people, both in Greece, more than 400 people, both in Greece and Turkey. And our product mix serves construction applications, refractories, agricultural and chemical industrial applications. Concerning product types, around 40% we produce caustic calcined magnesia, around 70% dead bed magnesia, and another 33% basic monolithic refractories. The basic monolithic refractories are refractory mixes that are in the large part consist of dead bed magnesia. So the largest part of our product mix involves the production of dead bed magnesia. I will explain in the next slides how this differs from caustic calcined magnesia. And of course, around 9% of raw magnesite. We export all over the world. We are the biggest caustic calcined magnesia producer in the EU and one of the biggest worldwide. With our main market area is Europe, but also some significant activities in Australasia, Americas, and Africa. The general production flow sheet. The production flow sheet is rather complicated. I'm just giving a very brief and simplified overview. We have the mine, which in Gerakini, it is an open pit mine. It's basically the host rock, which is dunite, that contains the valuable raw material, which is magnesium carbonate. We have to mine it and extract the raw material, and then performed a series of comprehensive pre-beneficiation and beneficiation steps. to reach magnesium carbonate concentrate. These pre-beneficiation and beneficiation stages rely strongly on laser and optical sorting, state-of-the-art laser and optical sorting, and less on heavy media separation. Then the magnesium carbonate concentrates are processed in the calcination and sintering installation, which is with the heating of magnesium carbonate. Magnesium carbonate is transformed to magnesium oxide, and then the magnesium oxide product is finally processed to the end products. A few details about the calcination and sintering plant at Gerakini. As I said, raw magnesite has to be heated, thermally treated. In practice, this happens at our installation in typical rotary and shaft kilns. And the main product types, as I have already mentioned, are basically two: caustic calcined MgO and dead burnt MgO. The main difference is that caustic calcined MgO is a product that still has chemical reactivity and is thermally treated at relatively low temperatures. For example, the kiln peak temperature required is around 900 and 1100 degrees Celsius, while dead burnt MgO, which is a refractory product, which has to be chemically inert, has to be processed in the kiln with a peak temperature as high as 800 to 900 degrees Celsius, and can also reach 2000 degrees Celsius or more in certain cases. Now the heat goes for the, of course, for the decomposition of magnesium carbonate, where you had the emission of CO2, and these are the process emissions, and for the sintering of the magnesium oxide to form dead burnt magnesia. In that case, this can be highly thermally demanding. For example, for a certain dead burnt magnesia product, the consumption can be as high as 10.3 gigajoules per ton product, with associated emissions, total emissions, both fuel and process, as high almost as 2 tons per CO2 per ton product. So from the total energy requirement in the Gerakini plant, which is here 331 teracal per year, most of it is energy, is thermal energy from fuels, which is the largest part, and also from electricity. The associated emissions, direct emissions from fuels and for process, and indirect emissions from electricity. The direct CO2 emissions from fuels comprise around 43% of the total CO2 emissions, and you see that most of the associated CO2 emissions are the so-called process inevitable, which can go up to 50% of the total emissions. Of course, there are ongoing activities to reduce our greenhouse gas emissions. The first and easiest way, let's say, to do it, of course, is to improve the energy efficiency as much as possible by limiting energy losses through thermal insulation, through heat recovery, which in our case involves the utilization of flue gases used in preheaters, to increase the energy conversion by investing in new generation electrical motors and new mobile equipment, and of course increase productivity by increasing beneficiation efficiency and oil recovery. This means that if we minimize the amount of byproducts generated, then the conversion efficiency will also increase, and of course automation and process control. As a second measure is, of course, the increase the contribution of renewable resources, And this is my talk today. For example, the use of biomass as fuel. The third way is to apply circular economy principles, reuse and recycle of byproducts. Again, increase the conversion efficiency and the consumption of heat energy. And last but not least is to investigate carbon capture and utilization solutions. We participate in several European and national research projects because, as I said, even if we manage to 100% replace the use of fuels by renewable resources, we will still have a significant part of our CO2 emissions that will be from the that will be processed, that have to be captured and in order to be economically viable, utilized. Our targets in bamboo, of course, as I said, is increase the energy efficiency of the calcination department and globally the Gerakini plant, reduce dependence on fossil fuels by using biomass, and with the concomitant reduction of CO2 emissions using carbon neutral biomass. This also has the benefit of the reduction of NOx emissions, which we further help by utilizing low NOx burners, allow flexible energy consumption according to market prices, and also assess possibilities for waste heat recovery. Concerning biomass usage at our plant, just a quick reminder, the biomass is defined as the biodegradable fraction of products, waste and residues from agriculture, forestry, and related industries. In our case, this involves mainly wood chips and sunflower husk, as well as seasonal biomass, which is sawdust, olive kernels and cake, and pruning wastes. Of course, biomass types are restricted by their availability in required quantities. So even if sawdust and olive kernels are ideal biomass fuels, they are available in limited quantities. So we have to look into alternatives. Of course, from a technical point of view, a large number of characteristics affect the properties of biomass, and these will define its use and the technology used for the energy production. There must be careful selection, which is based mainly on chemical composition, moisture, and ash quality, as well as heating value, density, hardness, volatiles, and solid carbon content. For us, the most important characteristics are chemical composition, because the biomass is directly utilized as a fuel in the rotary kiln, and the flue gases and the biomass ashes come into contact with our end product. So we have to be very strict in having a biomass with low undesirable substances, low heavy metals, of course, chloride and fluoride. Moisture should be as low as possible, because high moisture can lead to complete combustion, low thermal efficiency, and low flame temperature. And of course, the ash content should be as low as possible, have high melting point and low acidity, because as I said, this may affect product quality and moreover damage the kiln lining. Therefore, the melting point of the ash is very important to us. From all the biomass is studied, the highest melting point is observed for the ash of wood biomass, with a flow temperature that can be as high as 40 to 1500 degrees Celsius. As I said, moisture strongly affects the heat value, and this is also an important parameter for energy production. indicatively for wood, wood can come into all varieties that can have biomasses with as high as 50 or 60% biomass. You see how much the low heating value is reduced. On the other hand, for the olive kernel, where the water content is less, that can range from 15 to 25% of moisture. Again, there is also a significant reduction in the heating value. Of course, this is as delivered. If we were to make a rough heating value comparison on an as delivered basis, of course, pet coke is the champion in our comparison here, with almost as 8,000 kilocalories per kilogram. And second and third, closely third, is the olive kernel and sunflower husk. Then with the sawdust and wood chips, the reduced sawdust and wood chips heating value observed here is mainly due to the large moisture contents, water contents of these biomasses. Now, if we were to make mass balance and calculate the equivalent fuel cost in each case, the fuel cost, of course, is the euros spent for every megacal or any other unit of thermal energy generated. We of course have to make an assumption here on the CO2 cost. These are two cases, 25 euros per ton generated, or 40 euros per ton generated. Of course, for the pet coke powder, you see that when you have the increased cost for CO2 allowance, then you have a significant increase in the equivalent fuel cost generated. Of course, for the case of biomass, the CO2 cost does not affect the cost of the heat generated, but you see here that the lowest fuel cost comes from the olive kernels, and then by increasing wood, sawdust, olive cake, wood chips, and sunflower husk, you can see here, of course, that the sunflower husk is competitive, of course, when we are dealing with increased CO2 prices, which will be the case anyway. How are we utilizing this biomass at Glacier Magnesite? We combust it directly with a co-firing mode. We produce a homogeneous mix of ground biomass and ground pet coke. We are striving to increase this up to 1:1 by weight, and then feed this to the rotary kiln burners. Of course, the biomass must be milled in a mill with the introduction of hot air to reduce its moisture. And on the other hand, the pet coke, the unground pet coke, which also has a significant amount of moisture, is also dried and milled. The extra benefits of this partial replacement of pet coke, of course, is the reduction of other pollutants like SOx, NOx, and carbon monoxide, with aiming, of course, to achieve the same flame stability. There is also another mode, which is co-feeding with raw magnesite. This is a special case for the wood chips. which are large in size. For example, wood chips as high as 5 inches in nominal size, having 25 to 30% moisture, can be fed 2 to 5% by weight of kiln feed. If this is a rotary kiln, you have the kiln feed magnesite, the magnesium carbonate, is made with wood chips and fed in this direction. This goes down in the rotary kiln. In the other end of the rotary kiln, of course, there is a burner where the raw material comes into contact with the hot flue gases. There is the evaporation zone here, which around 400 to 500 degrees Celsius, all of the moisture of the kiln feed is evaporated. And then there is a kiln feed zone at temperatures more than 600 degrees Celsius, where there is combustion of the wood chips. And this whole evaporation and preheating zone contribution helps us in reducing the thermal load required for the fuel injected through the burner. One of our main activities in Bamboo is design, construct, and test a low NOx burner. This we have already done. We have already designed it, constructed it, and tested it. We are now in the application phase. This burner, this is the entrance of the burner in the rotary kiln head here on the right. This burner is able to handle high biomass to petcoke ratios, and early trials indicate that we can achieve greatly reduced petcoke associated NOx emissions that can be as high as 40%. Here we have the cross-section of the burner head. What's so unique about it is that the burner, of course, the solid fuel is the mix of biomass and petcoke is transported with air through this section here, and the liquid fuel in the middle when it is used. And there is also the inner air here and the outer air. There is the design has an inner and an outer air swell adjustment, which can be let's say controlled by the degrees that these feeding pipes are turned. Increasing swirl generally helps you decrease NOx emissions. The biomass used at Gresham Magnesite has to meet several challenges. There is, of course, a grand limitation here, which has to be stressed. This main limitation resides in the high temperatures required to produce dead burnt magnesite, which are close to 2000 degrees Celsius. This cannot be, unfortunately, be accomplished without conventional fuel participation in the mix. There is also, as I mentioned, the high fuel specific consumption, which means that we have to secure high volumes of biomass and, of course, handle. Making sure that the product quality is preserved. I mentioned the direct firing mode, the flue gases and the ash from the biomass will come into contact with the raw material and the product. And of course, due to the high temperatures required by the process and the generation of ash, there is damage risk to the kiln internal lining. Our immediate planning for 2001 and the period between 2021 and 2025 is, of course, maximize co-firing ratio of biomass in the rotary kiln fuel mixture as I said, taking into account existing technical limitations without compromising product quality. The specific objective is to replace at least 10,000 tons of pet coke with approximately, as we currently see it, with 20,000 tons of sunflower husk pellets. If possible, we will produce caustic calcined magnesia, depending mainly on biomass consumption. Unfortunately, the production of dead burned magnesia will still rely on conventional fuels. Currently, we have large-scale industrial trials underway where the sunflower husk is milled, mixed with ground pet coke and fed directly, and the parameters monitored and evaluated include the contribution of the sunflower husk, the flame temperature achieved, the gaseous emissions, the SOx, NOx, carbon monoxide, the organic carbon emitted, and of course, continuous product quality monitoring to see if the quality is compromised. And of course, planning, because extensive use of biomass will necessitate the provision of relevant infrastructure, dedicated biomass mills, biomass pet coke mixing silos, pneumatic conveyed systems, weight feeders, etc. Thank you very much for your attention. I would be happy to answer if there are any questions in the audience. Thank you very much.
Okay, thank you very much, Javi. So this would be our last presentation within this Bamboo Project webinar. So if the audience has any question, we would be more than happy to answer them. Okay, of course, as previously said, we will share these presentations through the social media of the project. So we will, sorry, okay. So you can maybe contact us afterwards. Okay, sorry, I'm having some troubles. Okay. Anyway, so yeah, that's so no question. Okay. So thank you very much, everybody, for joining this webinar. We hope it has been fruitful and interesting for all of you. And we remain at your disposal for any further doubt or comment or interest you may have in the future in Bamboo Project and in the activities we are performing. Okay, so thank you all and have a nice afternoon.
Thank you very much.
Thank you very much. Bye-bye.
Thank you.
Bye.
Thank you.
Thank you. Bye-bye.
Thank you very much. Goodbye.
Thank you. Bye.
Bye. Thank you.